Okay, so you know what electronics is. I didn't even need to say that, right? Those are these gadgets that we love and hate. But of course, for electrical engineers, electronics is something more than just gadgets. It's also a tool perhaps to make a career with. We can invent new things and then use electronics. We can design it using this electronics. We can build it. We can sell it and maybe get rich with that. So let's ask the question: what is so good about electronics? Why is electronics worth to make a career around? Okay, so well, electronics can do a few things really very, very well. It's not unique. There are other ways you can do that, but electronics can do it particularly well. And so let's go and look at some of these things. So information processing. Right? Some of you have computers here. I'm sure all of you have computers, at least at home. We use computers to compute, read, manage, access, and so information. They're extremely good on that. Electronics is also an extremely good medium for storing things. Used to be books were the best thing. Now, if you want to carry around 1,000 books, well, you load them into an electronic device, right? As I said, electronics is by no means the only way on how to do computation. You could also use this beautiful mechanical machine invented by a man with name Babbage, and you could actually do additions with this. And it would take you only slightly longer than doing them in your head, or maybe it actually would be faster. Anyways, but with electronics we can do this much better, much faster, and also much less expensive. We have a chart here on the right side that shows the power of or the performance of CPUs that are used in our laptops. And look at that. They started sort of the first ones by a little company at the time, Intel, called 4004, was made in 1970 or 71. Right? And it was actually made. Do you know what the first application was of a microprocessor? It was a pocket calculator. A company, Busicom, they wanted to have a new pocket calculator, and some clever guy at Intel said, hey, gee, you know, rather than building a custom chip every time, maybe we could make something that was programmable. And so that was the first microprocessor. And since they made many more, and of course there were others also that made microprocessors, and they got faster and faster. So now these are the fastest computers we have. Right? So, and also the remarkable thing is that it just keeps going on. In fact, this line, if you were to continue it stopped here in 2003 or so. Now it's up here. Okay? So it keeps getting better and better. So, and the same thing, of course, you know about memory, right? You hardly could store a song on a little MP3 player, and now you can put your entire library, and the problem is how to pay for all the music. And so some people have to, I guess, download it for free. Okay, so electronics, it's a very powerful way of process and store information, manipulate information, and sort of arguably it's the most powerful man-made information processor there is. Okay, so that's a good start. Hey, you know, we have an edge there. If you use electronics compared to, for example, mechanics or pneumatics or smoke signals, whatnot, then maybe you have an edge over the competition. Communication, same thing, right? There are lots of ways on how you can do communication, and this certainly works. Maybe you should try it once. But this also works. That's now, well, almost 30 years ago. That's the first commercial cell phone, a terrible clunker hauling around, and the car battery that you needed to run it for more than 10 minutes and so on. But obviously, it keeps getting better. It has gotten better substantially over this, and it keeps getting better, right? So electronics is really great for communication, and you can still send letters. You can send a letter to your folks at home now, telling that you arrived well at UC Berkeley on the campus, and you're already in EE40, but you can do much more quickly if you use, for example, a cell phone. And there are now almost as many cell phone users as there is the world population. I suppose some people have more than one and others they have none. That's maybe not quite right. But anyways, the point is that electronics is a very, very good technology to communication. If you want to get information around, You have lots of choices, but most of the time you will find that electronics is really the best way to do it. Okay? So another edge, if you want to build stuff that needs communication, well, electronics is a good start. It's a very good, very strong candidate. Well, information processing, storing information, and also communicating information actually is pretty boring if you can't get any information in there and if you can't get any information out there. Imagine a phone that didn't have a microphone, a phone didn't have a speaker. Well, that wouldn't be much of a thing, right? But fortunately, electronics shines in that category also. Electronics is very good at sensing things and at actuating, so microphone and speaker we just mentioned. We can, of course, sense light. We can sense touch, right? Mice, when I was when I was an undergrad student, computer mice were just invented. Oh, wonderful thing. Now we don't have these clunky keyboards. This actually, anybody knows what this is? A paper punch. So it used to be in the 60s when you wanted to enter a computer program, you used cards that were about this size, and you made little holes in them all over using a big machine like this, and then the computer read in these cards. It's totally crazy, right? Nobody would do this anymore. Anyways, now you have touch, and when you want to rearrange your photos, you just grab them on the screen. Virtually, you can move them around. So another thing, anybody has an idea what this is? Yeah, it's kind of the opposite, kind of opposite of a touchscreen. Actually, it's something that we may be looking at this. There are two types of projectors, right? We are looking at these projectors, and there is something in there that makes it that the right amount of light and the right color hits every pixel here on the screen. And how do we do that? Well, one of them is an LCD, which is really a transparent panel that can be made opaque. Okay? And the problem with LCDs is that they don't let a whole lot of light through. Even if they are made translucent, then they absorb like 99% of the light. So here is another technology. Here, these bluish plates, they are about 20 micron on a side. So 20 by 20 micron. That means that on the width of a hair, you would like fit 5 of them. Okay, so pretty damn small. And they can be tilted. There is electronics underneath it that makes them tilt, and that makes the light either go to the screen or go to the side. And when the light hits the screen, well, then we see it here. And so they twiddle very quickly. Of course, it's electronics that does the twiddling and so on. After all, electronics can do all the information processing and so on. We'll figure out how it does that. No sweat. And then we get this beautiful image. It's actually mirrors that are sending little packets of light to the screen. And why do they twiddle very fast? Well, because if you want to have a pixel that is half, that is not either gray, not white, or not full bright, or not full dark, what are we going to do? Well, we shine the light half of the time to the screen, and half of the time we send it somewhere else, and we do that with a frequency that the human eye never could notice, and constantly looks like gray, or any shade in between. Huh? So electronics is really great at sensing and actuation. So this would be an actuation example, right? We can do all of this stuff with electronics, and we're going to talk about how electronics does this. Some of these things, not less about the paper punch, of course. That's more of a joke showing how we progress and actually keep progressing. We'll talk about that too. We can do many more things now. We can, for example, use electronics to detect DNA, viruses, and so on. Some of my grad students are working on that. Obviously, we can get barometric pressure. What else? Actuators, ultrasound. We can image we can build an artificial bat. Turns out the bat is very useful. A colleague of mine, he builds helicopters that fly around in rooms in order to explore maybe a factory where there was an accident. It's poisonous. Flies around in a room, and he says that, even though he can mount a camera on his helicopter, he cannot really see the wall, because if the wall is all white with the camera, all he sees white, and then crash, nothing anymore. Right? So, but of course, if you have an eye like a bat that uses ultrasound, you can see the distance of the wall. It doesn't matter whether it's white or gray or black. Okay? And with electronics, you can do that. It takes a lot of electronics, but as you've seen with processor, we can make a lot of electronics, and every day we can make more. So electronics is also the most versatile, I would argue, man-made technology for interacting with the environment. So to to make it interesting, right, you have to somehow know what's going on there outside the electronics, and you have to somehow influence it. And electronics is very good at that too. So what do we have? We have a medium that allows us to do computation and management of information, that allows us to do communication of that information over wires, or also wireless, and it allows us to interact with the environment. And these three things together give us a tool in our hands that we can be very, very creative with, right? If you have the right idea, you start a company after EE40, or maybe after you get at least your bachelor, right? You start a company and you create that, and mankind will thank you for it. And you know that. Huh? All right, so it's a really wonderful technology, and there are lots of things that we can do with it. So how does EE40 and electronics fit into electrical engineering? So electrical engineering, just like probably every field, right, you sort of have ideas, and then ultimately have a goal, right? You make something. That could be a product or a vision or whatnot, right? So realize something. And in between, if you're an electrical engineer, well, in between is electrical engineering. And so what is electrical engineering? Well, I've split it up sort of in three broad areas that nicely fit together. Usually, every project needs really a part of all of these three areas, sometimes a little bit more of one or the other. So the first one is the physical layer. Of course, I mean, if you invent a nice algorithm or so for a computer, well, you still need a computer in the end, right? Likewise, a cell phone or so, well, to communicate, well, you need that. At some point, there is a physical layer, and that's EE40, right? We're going to talk about the physical layer here. We're going to talk about how to actually make it. Why does it even really, what's going on in that computer, right? How does it do all the things, and what things can it do? And then there is the system layer, and that talks more about the algorithm. Like, for example, we are here about 160 people, and probably most of us have a cell phone. If we so wanted, we could all start making calls. Now, that might not work so well. We should try it once. But at least many of us could make a call all simultaneously. Well, how do you make it that all these calls don't get one big mess, right? If we always started talking, it would be certainly very hard now to figure out any message, right? But if we did this on the cell phone, well, if we didn't shout too loud, then, in fact, we all could talk simultaneously, and we would talk to different people, and the messages would get across. They all go through the same air here, if you want, as my voice now, but somehow they don't get mixed together. And how do we do that? And, well, there is some physical aspects of that, and then there are also, of course, lots of systems protocol how to do that. Maybe you could do it that one person talks while the other one is quiet, and so on. There are more fancy techniques. All of that, for example, that's done in that systems layer, and EE20 would be a class where you learn sort of fundamentals about that system, many aspects of that system layer. And then there is, of course, computation, programs, and algorithms, and there you have even three classes, CS61, ABC, that you learn about that layer. So again, if you want to create something as an electrical engineer, then you may have your focus on one of these areas, or maybe somewhere in between or so, or some maybe a little bit on the corner or so. But generally, you will need a combination of all of these. Maybe you will be working. Maybe you are the specialist in the physical layer, but you will be working with somebody who writes all the programs, or vice versa, right? So it's really all these areas that mix together, and we'll get you the whole picture by having several classes in all of these areas, and then you can specialize. All right, so that's how EE40 fits in. Are there actually any questions already? All right, so they will come probably. So now, of course, maybe I already tried to motivate that a little bit, but there is, of course, the question, well, really, what am I going to learn in EE40? And I know that you have to take EE40, and but nevertheless, it's sometimes good to sit back and, is there actually, aside from fulfilling a requirement, is there actually something that I can learn in this class that I may be able to use later on? Okay, so now what exactly you will be getting out of EE40, frankly, it will depend on what your careers are going to be like and what your interests are and so on. So I can't really tell you what is the right answer for you, but I can give you a few possibilities, and maybe that gives you ideas of what it might be the right answer for you. So the first is kind of obvious, technology career. You might be interested in actually creating new technology, right? We've seen that, for example, microprocessors keep getting better and better. Well, why do they keep getting better and better? Because we make better and better technology, right? And somebody, of course, has to figure that out. We make better transistors, go faster, that are smaller, that take less power, and so on. Here is one view of looking at this, actually not drawn by an electrical engineer, Richard Smalley from Rice University. He's a nanotechnologist, if you want. So he shows things on a size scale. At the top is centimeters or so. There we can... well, there are lots of things, and there are ants and so on. There, here is natural things that are bigger and then smaller, and here are man-made things that get smaller and smaller. So the centimeter level, and then down here we are at 0.1 nanometers. So that's down on the atomic level, right? So and interesting enough, electronics started out the first transistors. Anybody has an idea how big they were about? First integrated transistors, few 10 microns on the side. And now how big are transistors today? Intel made just before Christmas, I think, they made an announcement. The 32 nanometers, we'll look at that, what that really means. But now a transistor is actually, the length of a transistor is 32 nanometers. How does this fit into place? Anybody knows the diameter of a hair? The diameter of a hair is about 100 micron, or tenths of a millimeter. So now if we go down from a millimeter down to nanometer, we really go down a million times, right? Sort of a millionth of a hair. Okay, so we increasingly make smaller stuff, and actually one of the problems that we're running into is now that these small transistors, they get on the scale of a few atoms, right? And so there is a lot of work now. Well, how can you make it even smaller? And actually there is one other thing that people are working very hard on. What could that be? Power dissipation, right? That has become the most important limitation. We could make faster computers. We could make computers that go at 10 gigahertz, for example. How fast does your computer go? 2 or 3, right? This one goes at about 1 or so, right? So a few gigahertz. Why don't they go at 10 gigahertz? Anybody has an idea? Yeah, exactly. There is no way to get the heat out. You can make it go at 1 gigahertz, then it gets so hot it just melts. It gets hotter than a nuclear power plant inside in that area. The power density would be more than a nuclear power plant. There is no way to get that heat out fast enough so that it doesn't melt. Okay? So we can't make it that good. We could design it, but we couldn't turn it on. And so then, of course, there's no point. Yeah, would make a beautiful picture. But so here are a few beautiful pictures. The one at the top, that's a Sun UltraSpark. So that's one of these CPUs. And the one down here is actually one that we made here. So this is an acceleration sensor, so that it can sense as you're moving and tilting and so on. You could use it to, the Wii console, right? This Wii game console. I never played with it, but some of you have, I'm sure. That one actually uses inside accelerometers. Not these accelerometers here, because we built them over 10 years ago here at UC Berkeley. And then there were companies like Analog Devices and ST Microelectronics and said, well, gee, that's interesting stuff what they built there at Berkeley. And we built it too, and they built it also much better, and they sell it now. Okay? So, you might envision a career that you are actually the one who builds the next accelerometer, and probably will be not an accelerometer, right? Maybe it will be a device that detects disease or so, or whatnot, right? There are lots of new ideas, or a camera that works like a bat. But you may, on the other hand, you may also say, no, I really want to work more on a systems level, much like E20. I'm interested in sensor networks, for example. And up at the top, taken one of the typical schematic diagrams on how these sensor networks are. Right? There is a cell phone that somehow interacts with them, and then there are all these wireless sensors that are linked together and also linked to the Ethernet and so on to the web. Down at the bottom here, we have an example of one of these things. And of course, there's a lot of algorithms, a lot of programs and so on that make these tick. But lastly, of course, there is hardware that they run on, and if you want to make it interesting, very often you have to add some new capability, like, for example, here they added this dome so it can sense light and maybe find out where the sun is or whatnot. If your focus is in the systems area, sort of EE20 and then the 120 series, well, then you still will be involved regularly with electronics. We've already talked about this question of how do you make it that we all can use a cell phone simultaneously and we don't get one big mess. Well, that again is something where the hardware obviously plays a role, but there is also lots of algorithms that you implement with systems technology. So even though when you build systems, your focus, of course, is on the algorithms, then these algorithms, they really are constrained and therefore tightly interact with hardware. And it's good to know what these constraints are so that you can build something that observes these constraints but also somehow does that in a way that it doesn't constrain the system performance too much, and therefore you can make something that's better than maybe your competitor. Okay, so the one area that maybe is farthest away in some ways is software engineering, right? Obviously, you can write programs. The programs are pretty useless if you don't run them on a computer, but you don't need to know a whole lot about the computer in order to run that program, right? So even though maybe you've never designed one, well, you can use it. So the question is really not, do you need to know anything about hardware when you want to be a programmer? The question is more, can you maybe be a better programmer if you know something about hardware, right? And so I listed a few things that are just happening now or have been happening over the last few years. Like, for example, computer CPUs, they dynamically adjust the supply voltage now in order to, and also the clock speed to conserve power. It's very important. The CPU that you have in your laptop, when it's not doing much, like, for example, suppose that you all closed it. That's very nice of you. But if you were to well, maybe one of them. If you have it sitting in front of you, but you're not really interacting with it, then it really doesn't need a whole lot of compute power. Now, only a few years ago, the computer had two modes. You could turn it on, or you could turn it off. And obviously, if you turn it on, then it runs full blast, always at the same speed, 1.6 gigahertz or whatever it happens to be, right? And it has a program called idle or something like that. It just executes that program idle that dissipates a lot of power, and it does absolutely nothing. Okay? Except it does absolutely nothing. It drains your battery, right? And also it causes global warming and all of these bad things, right? So now what CPUs do is that they you crank them harder or less, you can shut down certain pieces of like if you have a multi-core, you can say, well, now I'm really needing only one or two cores, and then you shut down the other ones. You can even shut down caches, and so it gets pretty complicated. You can adjust the supply voltage. If you have less supply voltage, it dissipates less power, but it cannot go as fast, so you have also to reduce the clock. And of course, then in the end, you can dissipate less power. It's very significant what happens there. The CPU of your computer, when it's not doing much, it may be using 1 or 2 watts. And in that same laptop, when it's running full bore, we will be running SPICE simulations and so on for this course. When you need all the cycles, or you play a game, right? Then it cranks up to over 50 watts. So the amperage that runs into your computer chip, and the little computer chip that's inside your laptop, it can vary between 1 amp or so at 1 volt at the low end, and can go up to 50 amps or 80 amps. Okay? And it does this dynamically. You definitely do not want to run it all the time at 60 amps because it also would get too hot. But sometimes it's good because now you have this whatever thingy running over your screen for your game, and it better be displayed correctly, right? So obviously, if you know about the hardware, if you know these constraints, well, maybe then you also figure out ways on how to build your programs that they exploit this feature very well, so that they use all the resources that your computer can provide optimally, but they use them only when they really need it, so that it doesn't dissipate much power, but it still works very well. Of course, you know that nowadays when you buy a computer, it's not faster than the one that you bought last year or 10 years ago, whatever. Actually, maybe a little bit slower. But it has more than one core. What does it mean that it has more than one core? Yeah, it basically has more than one brain. Right? It has two things that can do additions, if you want. Right? And it has two things that can push data around. It really has two CPUs in it. And so why is it that we used to simply make computers faster and faster? Why do we now put in multiple cores? Well, of course, the reason is power, right? But exactly how this works is very interesting, because it turns out that sometimes you do have a choice. For example, in an embedded application or so, you might use one CPU that goes at 1 gigahertz. You definitely can buy that, right? Or alternatively, you could get two CPUs that run at 500 megahertz, so just half, but you need two of them. So then together, if you can figure out a way on how to do the work in parallel, for example, it's a video processor, then you need two, but they run at only half the speed, each of them, right? So now the question, of course, is you have now two possibilities, right? Two design options. One of them is one processor goes at 1 gigahertz. The other possibility, you have two processors, and they run at only half a gigahertz each. So together they do the same amount of work. So which one would you pick? The two? Why? The what? Oh, okay, fine. Actually, today 1 gigahertz really is not the problem anymore. Plenty of vendors. But there's another reason. Yeah, power. Power. It turns out that one of these solutions has significantly less power dissipation. Which one? Yeah. Two that run at half the speed, they dissipate less power. Why is that? Isn't that amazing, huh? Well, in a nutshell, it is that power goes with voltage square, but speed goes only with voltage, linear in voltage. That's the reason. But now I understand, hey, I'm not going to try to wrap up half of EE40 into just one sentence. We'll get there in due time. The purpose of this slide is to motivate you. There is something in it for you. Even if you want to do software, well, there are some things that are quite interesting that actually affect software very profoundly. Then of these things you could say, well, these are old hats, we kind of know this now and we're done with, right? We sort of wrote it up and we've abstracted from this. There are probably abstraction layers in modern operating systems that deal with all of this stuff. The thing is that things like that, they get invented all the time. 5 years ago, you didn't have this, right? So what do you have in 5 years? Well, I don't know. It's going to be something else, but it's going to have to do with hardware. In order to understand what's going on, it's going to be helpful to have an idea of how this hardware really works, so that you can read those articles too and understand and be the first one to find a clever way on how to make your software be better than if you just program the way you did 10 years ago. Okay, so then there is, of course, hey, we're electrical engineers, and there are some things that are really good to know, and so maybe that alone is a reason to actually know a little bit about all facets of electrical engineering. So I just list one example here, and I start on the upper left hand there with two quotes. One of them is from the chairman of IBM at the time, a very powerful company, right? And actually, this Thomas Watson, he really converted IBM into this extremely powerful, most powerful at the time technology company. And what he said is, I think there is a world market for maybe 5 computers. Okay? He said that in the 40s. It's true. Then the second quote is actually not the correct one, but it's attributed to Bill Gates, who disputes it. He said 640K ought to be enough for anybody. What does this quote refer to? The Gates or the Microsoft, of course, started with the first PC, right? IBM made that first PC. Was a really big and ugly box that could do almost nothing, but at the time it was, wow, wonderful. It cost $10,000 or so. And Bill Gates, he delivered the operating system. At the time, it was called MS-DOS, and you still see it at the command prompter. So it's a terrible thing by today's standards, but then it was, of course, very powerful and so on. And this MS-DOS had a limitation. The maximum memory you could stick into your computer was 640 kilobytes. When the PC was new, it cost $10,000, but not with 640 kilobytes of memory. No, with probably 64 kilobytes of memory. So only somebody really, really, really rich could afford 640 kilobytes. And so probably already because it was so terribly expensive, wouldn't have bothered getting all that, getting that much memory. But you know what happened? Of course you know what happened. What happened is this thing here. This axis here is the year, and this is the number of transistors that you can put on one chip. Now, why is this important? Well, because if you make chips, it's a little bit like printing, right? What do you have to pay? You have to pay for the paper. So if you can put twice as much text on the same amount of paper, well, you don't pay much more, but the cost really reduces. So being able to put more and more transistors on a chip allows us to put more and more functions, right? Really fuels this computer chips get better and better and faster and all of that. So this started in the 60s. Why did it start in the 60s? Well, that's when the first man, Kilby, he invented how to put 2 transistors on a single flat piece of silicon, right? And then now we can put how many transistors are in a? If you recently bought a decent computer, how many transistors are just in one the CPU chip? How many?
1 billion.
About 1 billion, yeah. Okay, so now we are up here. This line simply goes. The red line here, that's memories, and memories now are at 8 billion transistors per memory chip, while computers between 1 and 3 or so. And we'll be at 5 or 10 in a few years. Okay, so that's very, very interesting because, of course, we see that all along, right? If you were to look at the industrial age, right? Steel suddenly starting to be used more and more. There was typically that happens is referred to as S-curve. Typically, somebody has the idea, right, and then you're really sort of the only one on the block. It's expensive. We don't quite know how to do it yet, and so. But slowly and slowly, we understand. Hey, that's a really useful thing. You get more and more ideas of what you can do with steel, and then more and more people make it, and so on, and then it really grows rapidly. And then at some point, well, you sort of have done the kinds of things you can do with steel, and there is something new on the horizon, maybe plastic or whatnot. And then this S, or the slope, starts to decrease, and at some point, we reach a maturing stage, and maybe actually the output, that didn't happen to steel, but for other things, then the output actually decreases again. Okay, so typically, the middle part where you have really this strong exponential growth, it depends on what exactly it is, but typically it lasts for a decade, maybe 2 decades, but that's about it. For most things, you get this exponential growth for a relatively brief period of time, and then it stops growing exponential. Not so in electronics. In electronics, the number of transistors and therefore the performance, the things we can do with chips, so that keeps growing exponential since the 60s, since the first guy who figured out how to put more than 1 transistor on a chip. Since then, we've been growing exponentially. This is a log axis, this is linear, so it's exponential growth since then. People all the time, they've said, here, this is the ultimate limit, something, the wavelengths of light gets in the way, or some whatever artifact, or so some physics, the electrons can't go that fast, or Whatever, take it, whatever you want. People have kept predicting that's the end of it. And now, more than ever, we have a very long list of things why this is not going to go here, this is going to go like this, or maybe that, whatever, right? But I wouldn't make a bet on this slope changing significantly. Why not? So far it hasn't. And why hasn't it? Well, because people always had really clever ideas on how to extend it. What do we know? Maybe nanotechnology or whatever is going to be the next thing. Another reason to know about technology and to follow it, because I don't know where exactly it's going to go, but I can promise you there's going to be changes, it's going to be exciting, and the one who understands it and exploits the changes first and best is going to be the winner. So be prepared. Here are some immediate consequences of this exponential growth. The cost per function of a digital function, so if you need an addition or multiplication, so the cost for that function decreases by about 25% a year. Or the performance increases by a similar percentage every year. Year over year, it just gets better because technology gets better. Has been for 40 or 50 years now, and chances are it will be also for the future, at least for the foreseeable future. So that can have big ramifications. So first of all, you can make foolish statements like that, or well, maybe he didn't make the statement, Bill Gates, but he sure programmed into MS-DOS a limitation, right, that wasn't really a very good limitation, 640 kilobytes, my God. Right? So, and he certainly benefited from that not being a real limitation. He moved it in his later OSs, or Microsoft would be a very tiny, well, would have long vanished, right? But what does this do to your startup? Suppose that you have a really, really great idea and you can make something that two times better, maybe a cell phone that communicates at twice the speed or something like that. A few years when you build it, right? So you have an idea, a cell phone that really, the download, this 3G or whatever, the data download finally works, right? You can play real games or surf the web or so on your cell phone. It's a wonderful idea. So it's going to be twice as fast as you want. But now, how long is it going to take you to build this thing, right? You have to put together a startup company, you have to design chips, you have to get them into cell phones and so on. It's going to take a few years, right? Well, in that time, during all of that time, this thing is working too. So everybody, every year, is going to get 25% better. So very often, and I've seen this on and on and on, you look at the plan for a startup company, looks really, really impressive. And by the time when they finally have the product, they're actually 5 years behind their times, right? So it's good to know that it's good to not fall into these traps and to exploit them. Hey, not only do we have a clever idea to make it go better, but in addition, we also can exploit the fact that technology is going to be better by the time when we build it. Okay, so those are the kinds of things that we're going to talk about and learn about in this course. Now, how we're going to do that, much about the course organization you find on the web, and in particular, you will have to access BSpace. You all know how to use BSpace? Anybody? Not? Okay, right. So if you go to BSpace, you should have an EE40 tab. Click on that. If you don't have that tab, you need to tell myself or the head GSI, whom I'll introduce in just a minute, and then we'll make it that tab appears. And then you get the course overview and plenty of data about the course. Okay, so this is really convenient. Okay, so there are just a few things that I want to alert you to. You can look at details yourself. So there is a schedule there. The schedule has lots of useful things. It tells you more or less what you're doing in every lecture, but it also tells you when all the exams are. Go now, go to your website after the class, pick out these exam dates and mark them in your calendar so that you know that you will be here. Okay? It's very important. If you have a conflict, then you need to tell us now. Okay? So then we'll try to work it out. But if you don't tell us, well, sorry. Okay, so then we'll be about 160 students in the class and one instructor and 6 GSI. So we'll do as much as we can and really love to interact with you. We have office hours on every single work day of the week. So if you have questions, please come and ask them, and we'll clear them up. Also, if you have questions during the class, of course, stop me and clear them up, because probably your neighbor has exactly the same question. So there is no time wasted. Now I'd like to introduce the 6 GSI that we have here. E, where are you? So why don't you stand up here? They won't shoot darts at you, right? Okay, so E is actually the head GSI. So, for example, if you have a conflict or so, then you would go to E. For many things, you go to E. But, of course, if you have technical questions, then absolutely all of us, we are available for you. I put my office hour on purpose relatively late in the day. I have only 1 hour scheduled right now. But, hey, you know, if you come in droves, I'll add extra office hours. And for the GSI, it's the same thing. We will add extra office hours, right, Ida?
Hey, Mario.
We add extra office hours to help you with whatever questions you might have. Okay, so Ida, he's a lab GSI and also a researcher in my group, so he can tell you all about A to D converters and about biochips and so on. All right, Alex. Oh, Alex is back there. Okay, so a grad student this is your 3rd or 4th year?
It'll be my 3rd year.
3rd year. Okay, so he has really a lot of experience already about electrical engineering. So, you know, like every field, there is one view, and I've presented you sort of my view and my vision of electrical engineering. There are, of course, as many views and visions of electrical engineers as there are electrical engineers. So you might once, after figuring out all the homework questions, or so, might also ask Alex about what he's doing in his research and what he thinks about electrical engineering, what ideas he has. Jonathan, where are you? All right, so. And then Zhao. All right, and Ibo. Ibo, like E, have both taken EE40 a year or 2 ago and did very, very well in the course, so that's possible, and you can ask them how to do that. And, of course, you can also ask them all the questions about the course and the material so that you will do very well in the course also. Right? Any questions now? You will need a textbook, Nielsen and Riedel, and we assign reading from it, so you probably really need to have it. You can borrow it in the library, but it can be very, very inconvenient. Yes. Okay, so the question, could you also use the 7th edition? I really don't know. I don't even have it, and maybe you should compare the 7th edition with one of the other ones. But the thing is that we assign reading. We sometimes even assign examples or so out of the textbook, and then we say, you know, do examples 3.7 in Nielsen and Riedel, and we have to make sure that they are the same in both books, and so it's difficult to support multiple versions. We found that the 9th version isn't very different from the 8th, so that works. For some reason, the student bookstore tries to sell you an access code. You don't need it. So if you bought it already, figure out what it is, and if you find it real useful, I'd like to hear about it. Maybe then we can tell all the other students also what they could use the access code for. But if it just costs money, then don't buy it. Okay? Right? Yeah. So the text isn't perfect. I have a shelf full of different texts. They all have their pluses and minuses. So in the end, I had to make it. Yes.
So there's not really a significant difference between the 8th and the 9th edition?
I think the 9th edition is a bit bigger, but it's the same, page for page, almost the same, and maybe 1 or 2 chapters are different. All the assigned reading, I can promise, we checked it through examples, so they map 1 for 1. All right, lecture notes, what I just showed here on the screen, that you can also get on the course website. You can just get the PDF ahead of the lecture. So if you would like to mark it up and put it into your binder, you can download it ahead of the course. Sometimes 1 or 2 slides are changing because I make last minute, I have a flash of idea, and so then I'll put that in. But largely they are and then afterwards, usually when I don't forget and when I don't have a computer problem, I will do the marked up things on there also. But today I didn't mark up anything. So you can get the lectures there. Assignments, they by and large are online. There is a homework every week. But in addition to homeworks, there are also readings, and there are also labs. And so they happen very frequently. So you need to go regularly to the website, and you need to do all the reading. We'll always assign it at least 1 week ahead of time so that you have time to do this thing. But notice, for example, the first homework is due already in actually a little bit less than a week. It's going to be very, very easy. It tells about also its course organization and prerequisites, but we have to get that out of the way very quickly. So go over this. Then is R1 and R2. Those are readings assigned from the book, so you'll need to get the book soon. So the good thing about online homework is that you submit it online, then also the answers. It looks like this. And immediately when you submit it, you get check marks. What is correct, what is wrong. And then if you have something wrong, of course, you, for example, might come to our office hours and we can discuss it and figure out what's the problem and fix it. So sometimes that feedback doesn't work. There are new versions of Adobe Acrobat that somehow have a security feature, then the feedback doesn't work. There's some instructions on the web on how to get around these problems. If you can't fix them, then talk to us and we'll make sure that it works for you too. Very important, of course, for the course is laboratories. You will see again in the course schedule when these labs start. They start actually only a few weeks from now. Generally, you will work in groups of 2 in the laboratory. So if you do not have a lab partner yet, you have sort of a couple of weeks to find one. Try to do that. If you have difficulty with it, we will set up a site or so, a matchmaking site or something like that, and we'll help you. But so the laboratories, they're very important because really, just theory, in physical electronics, theory goes only so far. You got to build it. Otherwise, you didn't get the whole picture. So there is also a project where you're going to design your own thing, your own ideas, and we'll, of course, learn about that. Grades, I know they're very important, and so I give you the complete mechanism how to calculate your grade. So whenever during the course you want to know whether you're going to get an A+ or only an A, then you can use that algorithm and you can calculate what you likely are going to get. Okay? So, I think we'll need to talk about this next time. All right, see you Monday.